Chapter 7 for Stat 210 is all about the central limit theorem. So the central limit theorem is building off of the normal distribution that we've been talking about in Chapter 6, which is one of our continuous distributions that we've been kind of focusing on the continuous distribution since Chapter 5. All right, so Chapter 7, central limit theorem. In this chapter, we're going to learn how to apply and interpret the central limit theorem for means. And we're going to recognize the limitations of the central limit theorem, which that's going to be kind of important to understand because with our inferential statistics, we're going to be relying on the central limit theorem. So when the central limit theorem doesn't work, we can't do those things for any of our inferential statistics that rely on it. So we're going to make sure that we recognize those limitations. And this chapter is important to understand because the central limit theorem is what gives us the power to perform these hypothesis tests and other inferential statistics that we're going to do. And we're going to spend the rest of the semester doing that sort of thing. So central limit theorem. We'll abbreviate this as CLT, just so that we're not writing it out all the time, kind of save us time as we're writing. So the central limit theorem is one of the most powerful and useful ideas in statistics. What it says is if we collect samples of size n with a large enough n and calculate the mean of the samples and create a histogram of the means, then the histogram will be approximately normal or bell-shaped. It does not matter the distribution of the original population. So basically this is saying, you know, like I have like a whole bunch of you here, and I say each of you go out and collect a sample. Maybe we're studying the number of hours that students sleep. So I say each of you go out and sample maybe 30 people and just ask them, how many hours did you sleep last night? And then you're all going to come back and you're going to tell me just the average of the number of hours that everyone slept last night. Now, if I took everyone's average and I created a histogram of that, it would be approximately normal shaped, approximately a bell shape. All right. So the key idea here is that it doesn't matter the distribution here, that distributions of sample means are going to follow a normal distribution. Now, for this to work, our sample size n needs to be large, so at least 30, or the data originally, the original data that we were collecting from has to come from a normal distribution. So those are two things that we got to keep in mind. And also when we're doing our sampling, we're doing sampling with replacement. So sampling with replacement means that it's okay if, you know, two of you collect the same sample. That's allowed. So it's like when you're drawing the names out of a hat and you draw a name, you read it, then you put it back in before you draw for the next name. That's sampling with replacement. So it's okay if the same thing is sampled more than once. So with the central limit theorem, if you draw random samples of size n with a large enough n, then the distribution of the sample means will be normal, with the following being true. The mean of your sample means is going to be equal to the mean of your data values. So these subscripts are telling us what we're talking about. So mu is meaning mean, x bar is sample mean, x is data value. So the mean of our sample means is equal to the mean of our data values. The standard deviation, population standard deviation of our sample means is equal to the standard deviation of our data value divided by the square root of n. So the square root of our sample size. And then a z value, you're just using our z value, our z-score formula that we've used before, only now instead of data value, our data value is a sample mean. So it's sample mean minus the mean of your data values divided by the fraction, the standard deviation of your data values over the square root of n. Or you can look at it in terms of your sample means. So sample mean minus the mean of your sample means divided by the standard deviation of your sample means. Really, the big thing to keep in mind here as you're looking at this is these first two. Your mean stays the same, your standard deviation changes. It becomes the standard deviation divided by the square root of n. Now, when it comes to finding probabilities, we know the standard distribution. We know how to find probabilities within the standard distribution, and the central limit theorem gets us into the standard distribution. And in fact, using our z-scores, we can even get into standard normal distribution. Now, you only need to get into the standard normal distribution if you're going to use your table. If you're planning on using a calculator, you don't have to find a z. You just have to make sure that you make that change with your standard deviation. Instead of standard deviation of data values, you need standard deviation of data values divided by square root of n, because you're looking at the standard deviation of your sample means. So again, we're going to be using the normal CDF and the inverse norm functions as we're finding probabilities in the normal distribution using the central limit theorem. So let's run through a few examples here. So we have a manufacturer that knows their items have a normally distributed length with a mean of 6.7 inches and a standard deviation of 0.7 inches. If 18 items are selected at random, what is the probability that their mean length is less than 6.3 inches? All right. Reading through this, it's giving us some values. This first value, this is your mean of your data values. Then it gives you the standard deviation. Standard deviation of your data values. Then it's saying, okay, we're choosing 18 items. 18 items meaning 18 is n. And then it says, what is the probability their length is less than, the mean length is less than 6.3. So you're saying like probability, the sample mean is less than 6.3. Okay, so to be able to find that probability, we need to know how the sample mean is distributed. By the central limit theorem, since we started with a normal distribution, it doesn't matter how big our sample size is. We know that the sample means are going to be normally distributed. The mean of the sample means is going to be equal to the mean of the data values, and the standard deviation of the sample means will be equal to the standard deviation of the data values divided by the square root of n. So you'll see some notation over here. We're saying that X bar is distributed. That's what this squiggly line is saying. X bar is distributed. N stands for normal. And we have 6.7 for our mean and 0.7 divided by square root of 18 for our standard deviation. And we're looking for the probability that X bar is less than 6.3. So we can go ahead and use our calculator for this like we did back in chapter 6. So X bar less than 6.3, turn that into interval notation. We're saying from negative infinity up to 6.3. So our lower bound, our upper bound. And then our mean is 6.7. Our standard deviation is 0.7 divided by the square root of 18. Plugging in that into our calculator, we get 0.008. Now, of course, you could have gone through and done this with a table as well. You would have just needed to standardize before going to your table. In this next example, we're again finding a probability. This particular fruit's weights have a mean of 733 grams and a standard deviation of 13 grams. If you pick 54 fruit at random, what is the probability their mean weight will be between 728 grams and 738 grams? So we have the mean of our data values and the standard deviation of our data values. We have n. And then we're looking for the probability of being between 7.28 and 738. 728 and 738. Now, we have a large sample size. So since we have a large sample size, it doesn't matter how our data was distributed. We know that we can use the central limit theorem here. So central limit theorem says that our sample means then will be normally distributed with a mean of 733 and a standard deviation of 13 divided by the square root of 54. We're looking for the probability that the sample mean is between 728 and 738. So we have our lower bound of 728, our upper bound of 738. our mean of our sample means is 733. Our standard deviation for our sample means is 13 divided by the square root of 54. And our calculator will give us that this is 0.995. Now again, we could go through and we could standardize this. We could find a z-score for each of these and change this into the standard normal distribution and use our table. We could absolutely do that. So you'd just be finding the z-score for 728, the z-score for 738, and then using your table to find your probability. You can even think about your empirical rule and kind of give an approximate guess. For using the empirical rule, again, you're going to have to standardize because you have to think about the z-scores. And what you're going to notice is the z-score for 728 and the z-score for 738. They're approximately close to about -3 and about +3, which means we know that probability being between them would be about 99.7%. So about 0.997%, or 0.997, which is really close to our answer here. So thinking about our empirical rule, we'd say, oh, hey, yeah, that looks like it's a good answer. So that's kind of how we can use our empirical rule as a way of kind of gauging if we've got the correct answer or something at least close to the correct answer. The next example, the manufacturer that makes watches has a mean lifetime of 9.2 years, and the watches have a standard deviation of the lifetime of 1.4 years. If we picked 54 items at random, 9% of the time their mean life will be less than how many years? So we ask ourselves, can we use the central limit theorem here? Well, we have a large sample size, so yes, we can use the central limit theorem here. And the central limit theorem will say that the sample mean is normally distributed with the mean being 9.2 and the standard deviation 1.4 divided by the square root of 45. We're looking for the probability that x bar is less than little x bar is equal to 0.09. Now, on these, I tend to like to draw pictures. So I'm going to draw a picture for us here. We have a nice, pretty normal curve there. And we're saying we want some value that has an area to the left of 0.09. We are looking for the value that is there. We know the mean, 9.2. We know the standard deviation is 1.4 over the square root of 45. So we already have the area to the left, so we're not having to calculate anything. And drawing the picture really makes sure that we have the area to the left. So since we have the area to the left, we're using inverse norm of 0.09, saying that the mean is 9.2 and the standard deviation is 1.4 divided by the square root of 45. And we get that the sample mean that has 9% of the time the lifetime is less than this would be 8.92. So 9% of the time watches last less than 9.82 years. Now, why might this be useful to someone? Well, a manufacturer would probably, like to have some sort of warranty, because if you see that there's some sort of warranty, you're like, oh, hey, they're guaranteeing their product, right? Therefore, I should, want to buy it more than a product that doesn't have any sort of warranty or guarantee on it. And so the company, of course, doesn't want to lose money. So they would make sure that they set their guarantee, their warranty, for an amount of time where there's going to be very few times that they would have to pay out. So most of the time you're going to see, like, oh, your product lasts longer than what the warranty or the guarantee is because the company is not wanting to pay out. So like if you see that there's a 2-year warranty on a product, you could guess that the product will last at least 2 years for you. There's going to be a small chance that it's not going to last at least 2 years, but if it lasts less than 2 years, then you have your warranty that you can fall back on. So this is something that, a manufacturer would go through and kind of think, okay, I only want to pay out the warranty for 9% of my items. And so they would say, okay, well, I would need to set my warranty about 8.92 years. So then maybe they would set it at 8, maybe they'd set it at 9 years, just so they have a nice, pretty number sitting there. But that would be kind of how they would figure out what they would use for their warranty. So that would be kind of how it might be used in the real world. All right, another example here. So particular fruits' weights are normally distributed with a mean of 552 grams and a standard deviation of 33 grams. If you pick 18 fruit at random, then 19% of the time their mean weight will be greater than how many grams? So we're looking for what's kind of like our lower limit on the top 19%, the heaviest 19% of our fruit. So we're thinking, okay, we have a normal distribution, and thinking about this, what would be our mean for our sample means? Well, we can use the central limit theorem here, because we're starting with the fruits' weights are normally distributed. So even though we have a small sample size, we can use the central limit theorem. So we're saying that our mean is 552, the standard deviation 33 over the square root of 18. And we're wanting 19% of the time it's bigger than that. So we're looking for some sample mean there, where this area here is 0.19. Well, then what's the area to the left of that line? 0.81. So to the left, we have 0.81. So we know that our sample means are normally distributed with a mean of 552, standard deviation of 33 over square root of 18. We're looking for the probability of being larger than some value is equal to 0.19. That gave us the area to the left then would be 0.81. So we're able to use the inverse norm function then. So inverse norm 0.81, 552, 33 over square root of 18. And we get that the sample mean that has 19% of the time it's greater than this is 558.83. Now, again, if you're wanting to think about standardizing this and using your normal distribution table, you're just going to be using your distribution table to find the value inside that's about 0.81. Then you'd be setting that equal to x bar minus the mean divided by standard deviation, and then solve for x bar, you're going to get the same value. So you can use your table like we did in the first half of chapter 6, or you can go ahead and use your calculator, whichever you prefer. Now, the central limit theorem is pretty powerful, but there are some limitations to using it. So the central limit theorem works for any distribution as long as your sample is large enough. The less normally distributed a distribution is, the larger your sample would need to be in order for the central limit theorem to work well. Typically, we can get by with 30, but it really does depend on the distribution. If it's a distribution that's really heavily skewed, then you might need more than 30. And if it's a distribution that's fairly close to the normal distribution, maybe you only need 10 or 15. For the purposes of this class, we're always just going to say, if we have 30, we're just going to make the assumption that it's close enough, we have large enough sample, and we're going to use the central limit theorem. Sampling always needs to be done with replacement, so make sure that as you're sampling, if you're planning on using something that uses the central limit theorem, that you're sampling with replacement. Now, because the central limit theorem is so powerful, it does allow us to perform things like hypothesis tests and confidence intervals, which is where we're headed next as we start doing some inferential statistics.